About 1 in 10 people worldwide are suffering from hunger. At the same time, food waste is estimated at between 30 to 40% of the food supply. We can use emerging technology to reduce food waste by developing more sustainable and improved food supply chains. In today's workshop, titled Farm to Plate AI, we'll talk about ideas to enhance freshness and reduce waste with robotics and computer vision. Let's get to know the speaker team for today. I'm Shriya Zog. I'm a software engineer at MathWorks with a focus on cloud deployment. I'll go over the workshop setup and introduction. My colleagues Nayara, Maitreyi, and Kartiga will lead you through the workshop exercises. Nayara, would you like to start with your introduction?
Yes, it's very nice to meet you all, and thank you for joining the workshop. My name is Nayara. I'm a performance engineer at MathWorks with a focus on deep learning benchmarking and a background in a mix of electrical engineering meets economics. So I'm excited to be here and learn more with you.
Hi, everyone. My name is Maitreyi. I'm a machine learning engineer here at MathWorks. I focus on machine learning applications for code, so generative AI for coding suggestions and AI-assisted coding. I've been here close to 5 years, and before that, I got my degree in electrical engineering with a specialization in deep learning. I've previously worked on computer vision, and I'm going to be guiding us through the second exercise for computer vision today.
Thanks, Maitreyi. Hello, everyone. I'm Kartika. I'm a technical consultant at MathWorks, and I work with our customers mainly at the intersection of computer vision and AI. So I'm excited to talk about some related computer vision concepts with you all today.
Thank you, everyone. All right, let's go over the workshop setup now. Some of you may have already finished this as the setup instructions were shared as pre-work for the workshop, but if not, we can finish setting them up now. You will need a laptop with an internet connection. We will use a browser-based tool called MATLAB Online to run today's exercises. You can head over to this tiny URL, farm to plate wids 23, and download the detailed setup instructions. I'll summarize what these instructions are. First, you'll have to create a MathWorks account. If you already have one, you might be able to use that with the caveat that you already have licenses that today's workshop uses in your account. If you don't want to risk it, you might as well just create a new account instead. The next step is to activate the workshop license. When you do that, MATLAB Online will automatically try to port your workshop files over from our GitHub repository. Then for the last step, from MATLAB Online, run this setup command, farm to plate _ setup, to verify that your environment is set up. If at any point you need assistance, please put your questions in chat and we will try to get to them as soon as possible. Let's take a little less than 5 minutes for this setup. I think let's take one last minute to wrap up the setup. And you will have access to all of this workshop material for up to a week with the licenses. So if you don't get to anything immediately or you find yourself short on time for the exercises that we do in the next few minutes, you can always come back and take a look at what you might have missed. How many of you expect that when you go back and you open your fridge, you'll find something in there that has gone bad and you need to toss it out? That's food waste. The food supply chain from farm to consumers also faces the same challenge of waste. Nearly 13% of food is lost in the chain from harvesting to transport to storage to processing. Food waste is also the single most material landfilled and incinerated in the US. The future of global food systems is strongly linked to the development of sustainable, equitable, and healthy food systems that deliver food and nutrition security for all. Reducing and preventing food waste has global implications. It can increase food security, which will aid in achieving the United Nations Sustainable Development Goal of creating a world free of hunger by 2030. Minimizing waste also means less resources wasted, energy conserved that may ultimately reduce carbon footprint. In this workshop, we'll present ideas to optimize the food supply chain by following the journey of mangoes from farm to your plate. Autonomous robots, artificial intelligence or AI, and remote sensing technology can assist in improving farm operations using precision farming, can automate harvesting and grading, and can also monitor food quality during transportation. Using technology and reducing waste at each of these stages increases throughput. The workshop will showcase 3 hands-on exercises. The first exercise introduces a simulation of a drone that surveys a virtual mango farm. Since it's hard to bring an actual farm to you, we're using simulations. The drone uses LiDAR to detect obstacles and navigate its way through the farm. Now imagine this drone is equipped with cameras. The second and third exercises will use images of mangoes from the farm. In the second exercise, you use these images to count mangoes using object detection. In the third exercise, you use hyperspectral images and machine learning to monitor the ripeness of mangoes. For each of these exercises, we'll provide background information and instructions to run the exercises, and then you will have time to try them out on your own. Again, if you find yourself short on time, remember that you'll have access to these for up to a week, and you can always go back to them later. I'll now hand over to Nayara, who will lead you through the first exercise.
What is it that autonomous navigation means at a high level? And when you think about autonomous navigation, that's the ability for a vehicle to map the environment and reach a goal without a human. Now, what this vehicle looks like, or what the goal is, will depend on the application that we are talking about. I'm sure a lot of you have seen autonomous cars, for instance, and here the goal can be as simple as go from point A to point B, but the environment where these cars are is highly uncertain and full of different rules that it needs to abide by, which makes this a very technically challenging task. Another example are autonomous robots in a warehouse. And here the goal can be make sure the shelves are never empty. And the list goes on and on. Whenever you think about autonomous navigation, you can think about aircrafts, satellites, the little Roomba that you have in your apartment. All of those are examples of vehicles that have some degree of automation. And
Nayara, could you share your slides again, please?
yes, and for our exercise today, sorry about that, we'll be talking a little bit about autonomous navigation on a farm. So we'll walk through a simulation where we are using a drone to navigate on a virtual farm. And the challenge that we would like to explore a little bit more in depth today is the fact that farm configurations can be quite different. So maybe you have a farm where all of the trees are very nicely lined up. Maybe you are in a region with mountains, or perhaps you are in a greenhouse. The key takeaway here today is the fact that autonomous systems can be adaptive. And I hope you can see that through our simulation. All right, so since we are talking about simulation quite a bit, I would like to introduce you to our drone in simulation. And we're going to be working with a digital twin of a quadcopter, which is nothing but a flying drone that has 4 rotors. It is equipped with a range of different sensors, like air pressure sensors that help this drone be stable in air while navigating. And it also has some remote sensing capability. And more specifically, our drone will have a light detection ranging sensor that will help this drone make sense of the environment. And for all of the engineers out there, we know that when we're doing simulations, we do need to make some assumptions. So some of the assumptions that we have here today for our simulation is that we are only using a single drone. Also, we will have only static obstacles. And here we are considering our mango trees as our obstacles. We will explore different farm configurations, but those are all static. As I mentioned before, this drone will be using a LiDAR sensor to navigate the space. And this navigation will have an obstacle avoidance algorithm embedded in it. And the drone moves in a way that it takes what we call waypoints, which are points of interest in the farm, in a way that you want to have your waypoints to be able to see all of the trees in your virtual farm. In the way that, for example, in this first farm configuration here, you would expect this to be the path of your drone. In the second one, maybe this is what your expectation is. And thinking a little bit more about this LiDAR sensor and why is it that our drone needs this for navigation. So when you actually take your drone and take this drone to a new space that it's never seen, quote unquote, the drone may be surrounded by all of these trees, but it's actually unable to make sense about the environment. And what this LiDAR sensor does is it emits lights, and then this light will be reflected by the obstacles around the drone. And the drone can use this information to map where obstacles are and where is it that the drone is with respect to these obstacles. And that's how this sensor is useful for navigation here. And then this data set, which we call LiDAR point clouds, can be used to estimate the trajectory of the drone and also to create what we call a 3D occupancy map of this environment, something like that. All right, so we had a few, technical concepts flying around here, but with that out of the way, we can go ahead to our exercise 1. And this will be our simulation of our drone. So if you were already able to set up your environment and everything's working, you can follow along with me. But if not, as Shreya mentioned, you will have access to this for a week. So not to worry, you can always come back to this and try it at your own pace. And I'll also give a few minutes so that you can explore on your own too. So let me review some of the steps of this exercise here. So first, we will create a scenario for a regular grid farm. And the way to do it is if you have your MATLAB online open, you can go to the command window and type this command here, exercise1 _ part 1. With this, you have an app popping up, and it will give you this option to load a regular grid farm. So you can just click the button there. After that, you'll be ready to run the simulation for the scenario that you create. You're going to see a graphic representation of this farm where the circles represent the trees, the X's represent the waypoints. And to run the simulation, just click this green button. And when you do, it may take a little bit of a time for this model to fully load. So please be patient. So what's happening here in the background is that our model is taking all of the information from this app and incorporating that to all of the algorithms that we have within the drone. Now, once that's all fully loaded, the first thing you will see is this, which not to worry, you don't have to worry about all of these implementation details, but this is the model-based design that we have for our drone. And you can explore on your own later on as well. But what you will also see are 2 different views of your drone simulation. The first one, you have your virtual farm, and you will see your drone flying around. The second one is your LiDAR view, which will show you the point clouds at each single step of the simulation. So basically, what is it that the drone sees right now? So when you're done with all of that, you can always go back to the app, reset your scenario, and start all over again and explore different scenarios. At any time, you can feel free to just minimize this app. It's fine. You can always bring it up later. If you're unable to find it in your interface, you can go to the upper right corner of the interface. That's where you can see all of the windows that you have minimized. Okay, so this is just a brief explanation of this exercise. I'll leave a few minutes here for you to work on your own. If you do have any technical issues, let us know in the chat. Can we get a little show of hands on who has been able to set up your environment and access the workshop files, just so we have an idea about who's following along online with us? I'll give 1 more minute for you to explore. And one thing to note about this app is you're able to load a pre-built scenario that we shared with you there, both a regular grid and a non-regular grid one. But also you have the option to build your own. So you see an option to add the obstacles, which are the trees, and also your own waypoints, and just see what happens. Is the drone really able to adapt to the different farms without us having to change the implementation in the background? So that's something for you to explore. All right, so in the interest of time here, I will move forward. And as I mentioned, for this exercise, you should be able to explore different scenarios for your farm and kind of take a look about how different configurations actually affect the performance of this drone. And another question that I wanted you to think about it, for example, we did talk a little bit about the assumptions that we make because we're doing a simulation here. But if you were to bring this closer to a real world implementation, which other elements would you add to the simulation? And how is it that these elements would actually make this a more challenging navigation task? So just a few questions for you to think about as you work on this exercise and explore more. And as Shreya mentioned, our drone has the capability not only for remote sensing through a LiDAR data, but what if this drone actually has a camera built in? And this is something that Maitri will talk to you a little bit more about in the second part of the exercise on fruit counting.
Hey everyone. We're going to talk about fruit counting. I just want to take pause here and make sure I'm sharing my screen. Everyone can see the right thing. Yes, excellent. Awesome. So today we're going to talk about fruit counting. And you might wonder, why are we going to talk about fruit counting? And that's because fruit counting is used in every stage from farm to plate. So it's used on the orchards, during harvesting, all the way to the consumer market. Today specifically, though, we're going to count fruits while they're still on the tree. Here we see a picture on the left of mangoes in their flower stage. On the right, they're at the harvesting stage in the warehouse. But we're going to count them while they're still on the trees before being harvested. So how are we going to count these fruits? We're going to use something called object detectors. Now, for those of you who are aware of what object detectors do, this is going to be fun. For those of us who aren't, I'm just going to tell you what object detectors are. So basically, as the name suggests, object detectors are deep learning algorithms that are specialized for detecting objects in images or in a series of images. So here we're passing an image of a mango through this object detector. And once it goes through the object detector, we get coordinates for these boxes. And when we overlay these boxes on top of our original image, we see what objects are detected. Additionally, the output of an object detector is also labels for each box that it detects. So here we see that these labels are mango, and so all of these boxes with their labels show us where the mangoes in the image are. These boxes are called bounding boxes in literature, and that's a term that we're going to use more, so I want you to remember that. So how do we count the objects once we have these bounding boxes? Well, we simply count them. The number of bounding boxes will tell us the final count of the number of mangoes in our image. So there's a family of object detectors called YOLO, and we're going to use YOLO V4. This is the name of the object detector, and YOLO stands for you only look once. And that kind of pays homage to how it was trained. We're going to pass the image of mangoes through this YOLO V4 object detector. And on the original image, the boxes that we get out of our object detector, we're going to overlay it on top of the image. Now, you might notice that there is a box that is on a leaf, and I'm wondering what's happening there. So let's take a look at what the labels say. It says oranges, and the leaf is a banana. Now, I don't know about you, but that doesn't look like a banana to me. And those might pass for oranges, but I know for sure that they're mangoes. Now, why is this happening? Why are we seeing apples and bananas as the labels? Why is a leaf a banana? And that's because using YOLO V4 out of the box does not give us the desired results. This is because YOLO V4, the original object detector, is trained on this data set called COCO, which is Common Objects in Context, so COCO. COCO does not contain mangoes in the original data set. Therefore, it has never seen the label mango. So basically, it's kind of saying, these look like fruits to me, but I don't know what they're called. So it kind of says, okay, maybe it's an apple, or maybe it's an orange like we saw in the previous slide. But what this tells us is that there is some implicit knowledge that YOLO V4 has of what the visual characteristics of a fruit are. So since our model already sort of understands what the visual characteristics of a fruit are, but doesn't quite know that this is a mango, how do we go from, yes, this is a fruit, but this kind of fruit is a mango? And we do this through a technique called transfer learning. Now, transfer learning is a machine learning method where a model that is developed for one task can be reused as a starting point for a model for a secondary task. So we're going to use transfer learning to create our mango detector. So on the left side here, we have the source data that I described, which is common objects in context. It contained about 200,000 images, and it had images which had objects like cars, scooters, oranges, apples, dogs, cats, and such. Overall, it has about 80 object categories. Now, we take this original model that is trained on this data set of 200,000 images, and we try to transfer learn on this model with a smaller data set. And this smaller data set is mangoes on trees. And our target labels are mangoes. So we use transfer learning because we don't need to train a model from scratch in this scenario. And because our target data is a smaller amount of images, it is also beneficial because if we don't have enough data, the model might not learn enough. So using this pre-trained model on this larger data set is actually super helpful. So here, since we're using mangoes as the target labels, we're also doing one notable thing, which is that we're getting rid of other labels in our data set. Because suppose I show it an image of mangoes with a cat in the background. I don't want to detect the cat in the background because ultimately the way I'm counting the mangoes is by counting the number of boxes that I get from my model. Excellent. So I went through a bunch of things to quickly recap. We're going to count mangoes using object detectors. Object detectors are these deep learning models that detect objects. If we count the number of bounding boxes that this object detector outputs, we get the number of objects in the image. And finally, to actually label the objects what we want them to be, we use something called transfer learning. Now, with these three concepts, we're going to dive into exercise 2. In exercise 2, you're going to use YOLO V4 to count the number of mangoes in an image. The first part of the exercise, we're going to use an out-of-the-box YOLO V4 model, which has not been trained on a data set of mangoes to see what outputs we get. What I want you to look for in this part of the exercise is what has the model already learned? How does it know that these are fruits? Like what visual characteristics do you think it is looking for when it's detecting those boxes around fruits? So is it that there's a lot of green background, and when there's an orange blob around those green backgrounds, it's like, is that a fruit? So those are some of the things that you want to look out for in the first part of the exercise. In the second part of the exercise, we're going to use a transfer learned YOLO V4 detector, which is transfer learned on a smaller Mango data set. And I want you to notice if the transfer learned network is able to detect mangoes correctly. And finally, in the third part of the exercise, we're going to count the number of bounding boxes that we get from this transfer learned YOLO V4 detector. So logistics. This is a little different from the first exercise that Nayara walked us through. So what we're going to do is from your folder pane on the left side, you're going to open exercise2.mlx. You'll either double click it, and that should open up this exercise. For those of you who haven't worked with MATLAB live scripts before, they're like Jupyter notebooks. And so you get these neat code sections with text in the middle explaining what those code sections do. And how do you run these code sections is by putting your cursor in the section itself. And then on top here, we see the run section button. So place your cursor in a section and hit run section, and that should run the section for you. You can also run the whole live script by clicking the run button on the right. So again, to recap, part 1, we're going to use vanilla YOLO V4. Part 2, we're going to use transfer learning on our data set to count the number of mangoes. But I don't know if you've noticed this. There is some extra mangoes that we're detecting. And for those of you wondering why that happens, it's because we've trained our YOLO V4 on this smaller subset of mangoes, and it's detecting extra bounding boxes, either as overlapping boxes or double counting something. Now, remember when Nayara told you that when you take a drone and you're looking at it as a video feed and trying to detect the number of mangoes, what happens if you're double counting the mangoes? What happens if you get overlapping boxes? What if you're trying to count them at night? So those are just some of the things that I want you to be mindful of while you're training this and while you're using different images and seeing what results come out the other end. We're very happy to answer questions during the Q&A at the end, and please post them in the chat. Please post the findings in the chat as well. With that, let's work on exercise 2 together. You'll have 2.5 minutes because you have plenty of time after the workshop to get through some of these exercises on your own and just play around and experiment. Let's take about 45 seconds more. Okay, with that, I'm going to leave you with a question, and that is, what are some of the other tasks in this farm to plate pipeline that we could use transfer learning for? And I'm going to hand it over now to Karthika, who is going to talk to you about ripeness estimation using hyperspectral imaging.
Thanks, Maitreyi. All right, so moving on to the last part of our workshop today, ripeness estimation using hyperspectral images. Now, similar to fruit counting, ripeness estimation can also be used in all stages of farm to plate. For example, during harvest, it can ensure that the mangoes are picked at the peak of their flavor. And for example, in storage, it can help in understanding ideal storage conditions based on their ripeness levels. Now, here is a cell phone picture of 3 different mangoes. Can you guess what the age of these mangoes are? How many of you think they're 2 to 3 days old versus 4 to 5 days old? You can enter your answers in the chat. They were actually 4 days old. But as you can tell, it isn't very evident from the images what the age of these mangoes can be. That is because a cell phone picture usually has 3 primary bands, the red, green, and blue, RGB, that recreate what the human eye sees. But what if you want to or need to see more? Hyperspectral imaging uses thousands of specific wavelength bands to pick up that unique response that you're looking for. Now, these bands can include RGB, but it can also go beyond the visible spectrum into infrared and ultraviolet that are otherwise not visible to the human eye. So instead of just having an RGB image with 3 channels, hyperspectral sensors collect information as a set of images. Each image represents a narrow wavelength range in the electromagnetic spectrum. These images are then combined together to form a 3D cube, also called the hyperspectral data cube. Each wavelength can give you unique information about spatial, texture, characteristics. Now, since there are hundreds to thousands of these wavelength images, not all of them may be equally useful for our application here, which is ripeness estimation. We can pick and choose any 3 wavelengths and that we think adds the most value and combine them together to form what's called the falsified color image. You can think of it as taking a highlighter and highlighting certain portions in your textbook. All it does is help you help change the data in such a way that it is easily digestible by humans. Here is an example of falsified color images of an actual mango whose hyperspectral images were collected on days 1, 4, and 9 respectively. So from left to right, you can start progressively seeing the changes in the color, the texture, etc. So with that technical background in mind, let's move on to exercise 3. In this exercise, you will use machine learning to map hyperspectral fruit images with their age in terms of number of days. And I'll go through each part now. The format is going to be similar to exercise 2. So you will open the exercise 3.mlx file. To open it, you can double click on it. It should be placed under exercise 3_ripeness estimation folder. So in the first part, you will visualize and explore the hyperspectral cube. Running this section should generate a figure with the hyperspectral data cube. So you can feel free to play around with the sliders to see what in each image looks like. Each image corresponds to a particular wavelength. In the second section, you will visualize your own falsified color images. And here you can feel free to play around with the drop downs to select different bands and see how the colors of these images change based on the wavelength bands. In the third part, you will visualize features already extracted for you from the hyperspectral data. Now, why do we do this step? Instead of passing the entire raw data to train a machine learning model, we extract only relevant information. In our case, the relevant information is the mean value of each image. So you can see the graph plotted for the mean values of all the images against the wavelengths. I want you to observe how the curves change for each day, day 1, 4, and 8. These subtle differences that you see are what is going to be picked up by the machine learning model in the next step. In the final part, you will train the machine learning model using the features extracted from the previous step. Specifically, you will train the linear discriminant model. I won't go too much into the detail, but the idea is that the model learns the statistical patterns of each group to classify them into different classes. You will then finally use the trained data to test on an unseen fruit to see how your model is performing. So a quick reminder that to run any section, you can place the cursor in the section and then hit Run Section button at the top of the tool strip. We'll have about 2 to 3 minutes to complete the exercise, and you can get started now. We'll take 30 more seconds to wrap up the exercise. You can always do them at your own pace later after the workshop as well. All right. So moving on. Something that I want you to think about is how else can we use hyperspectral images, right? Do you think we can use it for quality inspection to inspect produce health, or can you use it to classify a fruit from another vegetable? With that, we hope you enjoyed exploring cutting-edge technologies that perform path planning and navigate with drones, count mangoes using AI, and estimate mango ripeness using hyperspectral imaging. What next? Use what we learned now in real world. It could be to count the number of people at a Taylor Swift concert or estimate tumor using hyperspectral images. Thank you all for your time today, and we would love to continue the conversation. Feel free to connect to us on LinkedIn and post on Twitter. And we're also happy to take any question and answer questions.
So, hello, and thank you so much to the MathWorks team for your workshop. So, I joined a little bit later after the start, but the workshop, I've seen it before. It was excellent before, and it was excellent again today. So, thank you to the members of the MathWorks team. So, Kartika, Maitreyi, Nayara, and Shreya, thank you so much for your expertise. As we look at the Q&A panel, it looks like a lot of the questions were already answered, but I'm going to go and probably be a little flexible and maybe ask a question or two that may be on the minds of the audience members. But audience members, if you have any questions, please feel free to visit the Q&A panel. So here's a question. In terms of the development of this overall application, how long did that take in terms of kind of a time frame? Was it a week? Was it a month? Did it vary? Who would like to answer?
Anyone I can,
I think oh, sorry, go ahead.
yeah, no, go ahead, Naira. I was going to say
Yeah.
it's not definitely just a week, close to a month.
Yes. Yeah, and also I wanted to highlight, like Shreya mentioned, it took a while, but also we wanted to make something that is, easy to run, and it brings like an easy example for you to just get a sense about the technology behind this, and so that you can explore more. And also we had a whole team of people behind this. It's not just the four of us who presented today. We had a team of people who were able to run the exercises and troubleshoot, find bugs, so that we could refine this in a way that would be relevant for different audiences. And I hope you all enjoyed this today.
Thank you very much, Nayara. And we have a few minutes left. So I'm curious about the following. So a lot of people who attended this workshop may be interested in actually presenting this workshop, maybe for their communities. And I'm wondering, is there a pathway for those individuals to do that? Who'd like to reply?
I mean, absolutely. They can always reach out to us offline, and we can see what the best way is. Or the goal of the workshop is to, bring awareness around these concepts to our audience. So, they can reach out to us offline, and we can see how we can share the material with the wider set of participants.
Thank you, Kartika.
Because I think one other aspect of this workshop is not just using these tools, but also trying to solve a problem that's so pertinent and important. So we would love to also hear from you all. How could you use this technology and what problems could you solve?
Absolutely. And there are a few questions that have just popped up in the Q&A panel. So let's at least go with one of these questions, and one of these questions you may answer offline. So one question that just came up is as follows. As you mentioned, Maitreyi, but why separate object detector needed for animals? Can't it be the same with different classes / labels, identifying mango plus any other class? So I don't know if Maitreyi would like to start or if anyone else would like to jump in. So Maitreyi.
Sure. Yeah. No, it's a great question. So, the reason that we want to separate the two is because for today's application, the one that we highlighted in the presentation, we were counting mangoes. And the way we were counting mangoes was by counting the number of boxes that our object detector outputs. So, when our object detector outputs, say, 5 boxes, and those 5 boxes are mango, 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 cat, dog, if we count the number of boxes, that's 5 boxes. And now we have counted 2 extra mangoes that aren't in the image. And therefore, you want to separate the two models. One is only for counting the number of fruit, where we're not even detecting the cats or dogs. And the other one is only for detecting the animals, for instance. I hope that makes sense.
It does. And within the interest of time, I have, let's see, let's go with one more question, then we'll shift over to the next workshop. So the next question is, I'm jumping to this one. Here we were focusing on nearly ripe mangoes. I'd be interested in seeing how this could be leveraged in optimizing inputs such as fertilizing, irrigation, etc. So I have a lot of thoughts in this question with a GIS background and AI background, but this is your workshop. So who would like to jump in, and then we can take it from there? Anyone from the workshop team?
Actually, would love to hear your thoughts on this.
Okay, so one of the biggest items related to this very important topic in this workshop is being able to find out information about vegetation health, for example. So in terms of finding out about vegetation health, one of the tools that could be leveraged is hyperspectral imagery, because there are a lot of different calculations that can be performed just having access to that imagery alone without, believe it or not, using AI. But you can also explore using AI to help out with, I'm going to say, land use classification and other similar applications. Now, how would that work? That would entail taking the hyperspectral imagery that you have access to and using that within your AI model. And specifically because of this application, you probably want to have a high level of accuracy. So my belief is, without knowing full details, is you may want to wind up using deep learning. So in other words, using a neural network that can take that hyperspectral imagery as an input to help out with classification related to land use or other similar applications. I'm hoping that information helps. And I'm just looking at the time. It looks like we are at time. It is noon Eastern time. I want to thank once again the MathWorks team, my Trey, Karthika, Shreya, and Nayar for sharing your expertise with us. The other big theme too is if you have any additional questions, there are going to be pathways to connect with each of the members of the MathWorks team. Thank you so much for your time.